In this lesson, we're going to talk about how you can use both the first and second derivative to help you in sketching functions. If you remember our previous lesson, we talked about using just f prime, and now we're going to throw in the second derivative and see how it's going to affect your graph. Before we can get into some problems, I need to go over a little bit of terminology and some theorems. We're going to look at what the second derivative does as far as your sketching. The second derivative is going to tell you about concavity. You really have to keep straight what all the derivatives are going to take. Second derivative is about concavity. And let's go back. Yesterday we talked about the first derivative. And you use the derivative, first derivative, to tell you about increasing and decreasing, and then also any local maxes and mins. All right. Along with the second derivative, not only does it tell you concavity, but it also will tell you something called a point, or if you have, a point of inflection. Okay. So we've got first derivative, we worked on yesterday, does increasing, decreasing, local maxes or local mins. Second derivative is about concavity, and if you have any points of inflection. Okay. Let's talk about how do you know concavity and whether you're concave up, concave down, and what is a point of inflection. All right, there's a theorem that says that if you take the second derivative and your y double prime is greater than 0, so if your second derivative, let's fix that, not third derivative, if your second derivative is greater than 0, then y is concave up. And if the second derivative is less than 0, then y is concave down. And then your point of inflection that we've talked about is just by definition the point where you change concavity. So it's the point where the function changes concavity. Now, not every function will change concavity, but if it does, the place where it changes its concavity is called the point of inflection. All right? So let's go ahead and look at doing some sketching with the concavity in the problem also. So yesterday, example that I gave you was y equals x cubed. We looked at the first derivative and said that if you did y prime, you'd get 3x squared. If I set that equal to 0 to get my critical points, I'm only going to get x is 0. So my only critical point would be 0. Now I need to point out, critical points are from first derivative only. So my critical point is at x equals 0. And then when we did our sign chart, we got positive, positive. Because if I pick a number less than 0, put it into the derivative, it's going to be positive. Pick a number greater than 0 and put it into the derivative, we get positive. So that meant that my function was always increasing. But now if I throw in the second derivative and see what happens, well, the second derivative is 6x. And I'm going to set that equal to 0, and I'm going to get that x is 0. Now that is not a critical point. Critical points are from the first derivative only, but those are possible points of inflection. So now we're going to make another sign chart, where this time we're going to use y double prime. Really important that you put your labels on these derivatives, okay? So my second derivative was 0 at 0. So then I'm going to do the same thing I did with the first derivative test, which is what we did back here. When we were figuring out when we were increasing and decreasing, we used the first derivative test that tells you if the first derivative is positive, you're increasing. The first derivative is negative, you're decreasing. So I'm going to pick a number less than 0, like -1. We're going to substitute it into the second derivative. We're filling in y double prime, you have to use y double prime. So I'll put in a number less than 0 and put in -1. We're going to get a negative number. Put a number bigger than 0 in, and we're going to get a positive number. So now that's going to tell me about concavity. Okay? So we are concave up anytime the first or the second derivative is positive. So that means this would be concave up from 0 to infinity. We'd also be concave down when the second derivative is negative. Well, that's going to be from negative infinity to 0. Now, when I look at my second derivative, I see there is a place where I change concavity. I went from concave down to concave up. So that's my point of inflection. Okay. So there is a point of inflection at 0, and now I go back to the original function. If I put 0 in, I get 0. So there's a point of inflection at 0, 0. Now what I have to do when I sketch this is try to combine these two sign charts into one picture. So just doing a rough sketch here. Plot, if we go back, and I didn't write down all of our information from yesterday, but this was increasing from negative infinity to infinity. It was never decreasing, and then if it's not switching from increasing to decreasing or vice versa, then you're not going to have any maxes or mins. So this thing is always increasing, but it changes concavity. So here's what's going to happen. We're going to be increasing concave down first. So that's concave down, concave up. So we increase concave down. So that's going to look like this. And then we're going to increase concave up. So we switch and we do that. And that looks like y equals x cubed, which we are already familiar with. Before we move on, let me take just a second and sketch what each possibility could happen here when you're sketching as far as concavity and increasing, decreasing. So you're kind of clear on those. If you were increasing concave up, okay, your picture would look like, or that section of the picture would look like this. That's increasing in concave up. If we were increasing concave down, then we might look like that. If we were decreasing and concave up, we might have something that would look like this. And then the last thing would be if we were decreasing concave down. And if you were decreasing in concave down, it might look like that. Okay? So those are your four possibilities for increasing and decreasing and your concavity. So let's take a minute, look at a couple other graphs. Let's try this one. Y equals 4x cubed minus 12x squared. So start with our first derivative. Y prime, we do all the same thing we did yesterday. It's going to give us 12x squared minus 24x. We're going to set that equal to 0. Then we're going to factor. We're going to take out a 12x. If I take out a 12x, I'm going to get x minus 2. Okay, then I'm going to get my critical points of 0 and 2. Make a sign chart. So this is my y prime sign chart. Now I'm working on y prime, so I'm going to substitute my numbers into y prime. So I pick a number less than 0, like -1. I'm going to get a negative and a negative. So that's going to be positive. Put something between 0 and 2 in, like 1. I'll get a positive, then a negative. So that's negative. Something bigger than 2, like 3, I'm going to get a positive and a positive. So that's going to be positive. So my graph kind of does this. We increase, then we decrease, then we increase. All right, so now I can write down. There's my intervals of increasing and decreasing. We're increasing from negative infinity to 0 and from 2 to infinity. And then we're decreasing from 0 to 2. Now we do have some local maxes and mins. So we have a local max at, right here, 0, put 0 back into the original, you're going to get 0. And then a local min at 2. And if I put 2 into the original, you should get negative 16. Now, I just want to point something out real quick. A quick way to do this, when you're substituting those in, use your calculator and store those values. All right, so what I'm going to want to do is take negative 2 and store that as x, since that's the number I'm substituting in. Actually, not negative 2. We want to put positive 2. Push enter. And now I can just type in the function, 4x cubed minus 12x squared. That is especially helpful when you're using negative numbers and having exponents. You don't have to worry about all those negative, or all those parentheses that you'd have to use. So negative 16 should be my y value. So my local min is at 2, negative 16. Now let's use the second derivative. So y double prime, this is going to help me with concavity. It's going to be 24x minus 24. Set that equal to 0. I can factor out a 24, or I could just solve for x. If I factor out the 24, I'm going to get that my only place where this could be equal to 0 would be at x equals 1. So I'm going to do a sign chart now for y double prime. So I'm going to pick a number less than 1, like 0. If I put it back into the second derivative, I'm going to get a positive, then a negative. So that's negative. If I do something bigger than 1, I'm going to get like 2, a positive, and a positive. So we are concave down, concave up. A little saying that I've heard before to help you remember those. It's concave down like a frown, concave up like a cup. So concave down is going to do something like that. Concave up like a cup. All right, so now I can write in my concavity. I'm just going to abbreviate that. Where are we concave up and concave down? We are concave up from 1 to infinity and concave down from negative infinity to 1. And we do have a point of inflection, and let's go ahead and abbreviate it also. We do change concavity at 1. Then I can put 1 back into the original equation. And I know that's not hard to do without your calculator, but just quickly review some calculator usage. 1, store as x. And now what I would like to do is just reuse this 4x cubed minus 12x squared. So rather than type that in again, push second and enter. That's not the line I want. Push second and enter again. And there it is. And now I can push enter, and I get negative 8. So then my point of inflection was at 1, negative 8. Now, this is the tricky part. I'm ready to put all this together in a sketch. Okay, so here's what I'm going to do. I'm going to try to combine my two sign charts into one. This is the way I normally do this. So let me get over to a new screen here. Here's your y prime sign chart. We had critical points of 0 and 2, and it went positive, negative, positive. Y double prime, we had just the 1 point, and it went negative, positive. Okay, so what I normally do is try to put these together, and I go back to my y prime because it's going to have probably more critical points, should have more critical points, and I'm going to just kind of draw in a little dotted line there, and I'm going to put a 1. That's where 1 would be on that number line, because that's my second derivative critical point. Everything to the left of that was concave down. So I'm just going to sketch in concave down or write in concave down. And everything to the right of that was concave up. Okay. And now I'm going to sketch this. And again, I'm just going to do a rough sketch on this. You're going to want to start using graph paper for some of these. First thing you want to do, plot your maxes and mins and your points of inflection. So we had a local max at 0, 0. And we had a local min at 2, negative 16. Let's do this down just a little more. We'll count off by 2's here. 2, 4, 6, 8, 10, 12, 14, 16. So at 2, negative 16, just a little more. Then we also had a point of inflection at 1, negative 8. At 1, negative 8. So here's what you're going to do. Read your chart. You're going to increase concave down first. So we're increasing concave down until we get to 0. Increase concave down. Then we go to decreasing, and we're still concave down until we get to 1. So we decrease concave down until you get to 1. And now you really don't have to force this. This just kind of happens on its own. I'm going to switch concavity now, and from 1 to 2, I'm going to decrease and be concave up. And you're going to see that just kind of happens on its own. So I decrease and I'm concave up. And then from 2 on, we are increasing and concave up. And so we increase and we're concave up, and it looks like that. All right, I'm going to do one last example. I showed you this yesterday why we wanted to look at concavity. And let's look at, kind of very similar to the first one we did. Let's say y equals x to the 2/3. Okay, if I take the derivative, I'm going to get 2/3 x to the negative 1/3, which I'm going to rewrite that and make that 2/3 cube root of x. Now to get my critical point, remember, we talked about critical points are what makes the derivative 0 and undefined. But when it's a fraction is 0 if the top is 0, and it's undefined if the bottom is 0. Well, nothing's ever going to make the top equal 0 because the top is 2. The numerator is 2. The denominator would be 0 if x equals 0. So that's going to be my critical point. So when I do my sign chart, I'm going to use 0. Then to the left of 0, like negative 1, if I put that in here, I'm going to get 2. Then on the bottom, I've got a positive on the top. That's positive. Over, that's positive, but then the cube root of negative 1 would be negative. So I'd have a positive on the top and a negative on the bottom. So that's going to make that negative. Pick something bigger than 0, and since we're doing cube roots, pick a nice number. Something I can do the cube root of. So let's do 1. You're going to get a positive on the top and a positive on the bottom. So I'm going to get positive there. So that I know that this thing decreases from negative infinity to 0 and increases from 0 to infinity. Then I'm going to look at my second derivative. So y double prime, so going back to this form, would be negative 2 knots, because I take 2/3 times negative 1/3, multiply tops, multiply bottoms, x to the, now I need to subtract 1. So I have negative 1/3 minus 1. So you can either do crisscross applesauce or negative 1/3 minus 3/3. And that's going to give me negative 4/3. And again, I'm going to rewrite that. So that's going to be negative 2 over 9. And it's the cube root of x to the 4th. So again, I find out what would make the second derivative 0 and undefined. Nothing's going to make the numerator 0. The denominator 0 at 0. Now, if you look at this carefully, you really don't have to substitute in numbers, because the only place that I really need to worry about is what's happening right here with this radical. That's the part that's important. That's where the variables can change. The negative on the top is always going to be negative. The 9 is going to always be positive, so just need to see what happens here. Well, no matter what number I substitute in, when I raise it to the 4th, it's going to be positive. Then I'm going to do a cube root of that, and it's going to be positive. So I have a negative 2 on the top, and the bottom's always positive. So these will be negative both times. If you don't catch that, you can always substitute numbers in and get that. So that means we are concave down always. So no concave up, and that means no points of inflection. So now if I sketch that, let's go back. We did have this, that this thing decreased and increased. So we should have had a local mean at 0 and go back to the original. 0 to the 2/3, remember, is the cube root of x squared, so that'd be the cube root of 0, and that's 0. So I do have a local min at 0, 0. And then I'm just going to put together my two sign charts. So my y prime went negative, positive. So it was decreasing, increasing. And then my concavity, if I put that in with that, at the same point, and it went concave down both times. So this thing has to decrease concave down till it gets to 0, decreasing concave down. Then it's going to increase concave down. Increase concave down. If you remember yesterday, somebody said this looks like a bird. And that's your graph of y equals x to the 2/3. All right, we are going to spend lots of time working on f, f prime, f double prime, and getting the sketches. So those of you that have been having trouble with this, or if you feel like, oh, I'm never going to get this, I promise you'll have lots of practice. It's not going to be as bad as you think. It does take a long time, as you've probably noticed, especially once we throw in this second derivative. You're going to find that a lot of these problems are going to take at least a half a page to a page to get them sketched.